Okay, so I was telling these guys up here. Yeah, so the final actually begins on Friday, so you'll see a portion of it, um, and to work on like before, and it'll be for regular problems. So you won't see any of the actual lightning round questions until the actual final on Wednesday here at 8 a.m. Um, so today is the last new material of any kind. So really, I'm combining the previous two sections, so it's not that new, but it's the last section. Um, so we're solving second order differential equations using Laplace transforms, non-homogeneous, where a right-hand side, g of t, is discontinuous, therefore you need step functions. So this is 6.4 to text, 5.4 to notes. So since this is the last new material, it is important that on Wednesday, that's review day. Bring your questions about the practice final, any part of it, and we'll use the whole time for that. Okay. And all I have for today is just a few examples of what we have here. So that should leave you ready, once you understand those examples, on the similar problems in the final. Okay. So we have second order E, and the right-hand side, g of t, is defined piecewise. So it's equal to 1 until 3 pi. And then after that, it's equal to after that, it's equal to 0. And let's see. I'll just okay. Okay. Initial conditions: y 0, 0, y prime of 0 equals 1. Okay, so first thing you always do in Laplace transform problems is rules for transforming derivatives. So Laplace transform of y prime, which you don't need in this case, but I'm writing it down anyway because you will need it in general, is s times the transform of y minus the value at 0. And one we really will need here, Laplace transform of y double prime is s squared y hat minus y prime of 0 minus s y of 0. Okay. So when we apply this up here, Laplace transform of the whole, actually, we're not ready to take the Laplace transform of the whole equation yet, only the left side. We need to be able to do the right side also. So for this part, we first express it in terms of step functions. So remember, turning functions on and off. So at t equals 0, you turn 1 on, and then at t equals 3 pi, you have to, yes, it does feel like a Monday morning, then you turn 1 off, and that's it. There is nothing else because it's equal to 0 from that point on. So the term it's going to give you here is, at t equals 0, you don't need a step function. So you just have 1. And then to turn function off, you need a minus. And then, because you're turning off at 3 pi, you need the step function at that point. So use the 3 pi of t. And then the function you're turning off, which in this case is 1. So what that means is, in terms of step functions, instead of this piecewise definition, we can say g of t is 1 minus u 3 pi of t. So now we can transform that as well. Any questions about where that definition in terms of a step function comes from? That's what we did on Friday. Okay. So Laplace transform the entire equation is therefore a rule for y double prime. Oh, and I'll fill in the values. Y of 0 equals 0. So that helps. And this is 1. Plus Laplace transform of y, which is just y hat itself. So that's the whole left side. And then the right side, we have Laplace transform of this. And we can just transform each term individually and then add or subtract. So Laplace transform of 1 is what? 1 over s. And then the Laplace transform of this is, because of the step function, you get an exponential e to the minus 3 pi s times the Laplace transform of this function, which normally need to express it in shifted form. Now in this case it's a constant function, so there's no need to do that. But it's this is the Laplace transform of 1, which again is 1 over s. The other examples we'll see will be more interesting in terms of getting the step functions in order. Okay, so now what we need to do is solve for y hat of s. So if I gather all of the terms with y hat of s in them on the left side, you have s squared plus 1 and then any terms over here that do not involve y hat need to be moved to the other side. They're just going to be this one. That'll be 1. Okay. So I'm going to have, well, this is still going to be there. Or sorry, this transform is still going to be there. So 1 over s, 1 minus e to the minus 3 pi s. So this is, we'll call this g hat of s, because that is a Laplace transform of g of t. And then from moving this term over to the other side, we get plus 1. So down there in the boxed off space is what we get when we transform both sides of the equation. And now we can just go ahead and solve for y hat of s. Any questions up to this point? So then here we just divide both sides by s squared plus 1. So then I have 1 minus e to the minus 3 pi s, 1 over s squared plus 1. And then we have plus 1 over s squared plus 1. Okay. Now that last term is going to be relatively easy to handle. It's actually going to fit one of our rules exactly. Now rules that you're going to need here is, well, that's before Laplace transform of 1 is 1 over s. We've seen that already. Laplace transform of cosine bt is equal to s over s squared plus b squared. Laplace transform of sine bt is equal to b over s squared plus b squared. And finally, Laplace transform of step function times shifted function is equal to e to the minus cs Laplace transform of f unshifted. Okay, so we're going to be using all 4 of these rules going backwards. Okay. Now, so this term right here, this is the easy part. No pressure. What would the Laplace transform of that term be? Just by fitting it to the rules over here. Yeah, just sine t. And because we have s squared plus 1 in here, you can expect that's going to pop up again, or maybe cosine. But for this part, where we have 1 over s times s squared plus 1, we have a little more work to do first. And what do we need to do to that? So we've done in other problems. Because there's a product of functions that can be transformed. Almost. Yes, we're using partial fractions, but, and I think we've not seen this yet, when there's a irreducible quadratic involved, yeah, you do have that, constant over s. When there's an irreducible quadratic, you have a linear function up top. So this one's kind of a pain. So now if we multiply both sides by the denominator, we get 1 on the left side, and we get a s squared plus 1, and then we have bs plus c times s. Now, in this case, there isn't really any convenient value of s that you could substitute. Maybe 0. That that actually would help. So if you set s equals 0, then you get 1 equals a times 1, and then this whole term is going to go away. So at least that reveals what a is. All right, so a is 1. And then, as for the rest of it, another approach you can take, especially when there aren't any super convenient values of s to substitute, is just go ahead and expand this whole thing and match up like terms. So now that we know that a is 1, we have s squared plus 1, and then we have bs squared plus cs. And these have to match for any value of s. So if I group like terms, then we have 1 plus b s squared plus cs plus 1. And I could write this as, you can think of it as 0s squared plus 0s plus 1. And just match up the coefficients. So what does that tell you about b and c?
B is -1, C is 0.
Yeah. Okay. So everything is separated. So one thing so if we had gotten non-zero values for b and c, the b part would have led to a cosine, and the c part would lead to a sine. But we're not going to have that cosine part. So okay. So now for this term over here that has the okay, I'm going to distribute that fraction there. So I have 1 over s squared plus 1 plus, or minus, e to the minus 3 pi s, and then have plus 1 over s squared plus 1. So now using what we have there for partial fractions, so we have 1 over s, and then b is minus 1. So I have minus s over s squared plus 1. And then the same terms again. Okay. Let's see. Oh. Oops, actually, the cosine we're going to get is a sine that we're not, because c is 0. It's Monday. Okay, so now we can start inverse transforming. Now, the last term that was already handled, and this term, so inverse transform of 1 over s is
1.
Yeah. And then for the next term,
Cosine.
minus cosine t. And here, you can think of this as you're trying to fit this rule, obviously, because it's the only one that has a step function transform in it. So you can think of this as playing a role as f hat of s. So, and because you've seen this over here, you can think of this as the inverse transform of that. That is f of t. Now, so be careful now, when we inverse transform this, we're going to have a minus. And then this term we handled earlier, that is sine t. Okay, so now the tricky part. when you go ahead and inverse transform this, and you're fitting it to this rule, we know what C is, we now know what f hat of S is, so we also know what little f of t is. So what's supposed to go here? So you know it's going to be something of this form. Just have to fill in the particulars. And you're matching this against that.
Where does the U come from?
Well, U is going to be part of your result. All right, you're starting from here, working your way back to this.
U.
Yeah,
Just 3 pi.
just 3. Because notice there's a minus here and a minus here. Okay, yeah, U 3 pi. Yep, okay. What? I'm sorry, I didn't hear. Okay. Say again.
Is it f of t plus 3 pi?
It'll be minus 3 pi, but we know what f of t is.
Times 1 minus the cosine.
Yeah, this. So it'd be multiplied by 1 minus cosine of t minus 3 pi. All right. Okay. And you can you can stop here. The only other thing that could be done is cosine of t minus 3 pi using trig identities is cosine t cosine of minus 3 pi plus so that's cosine of 3 pi plus sine t sine of 3 pi. Cosine of 3 pi is minus 1, so you get minus cosine t. No, you don't have to do it on a test, I'm just pointing it out. Well, this could come in handy for instance if you're trying to match your answer against the one in the back of the book on a homework problem. Because they always manage to put the answer in some form that you would never get in a million years. All right, so questions about how this was inverted? So you have something like this, invert whatever's multiplying the exponential, that gives you your little f of t. Whatever your value of c here goes into your step function here and is used as a shift in there. Okay. Now, let's look at another. See if we can get that pattern matching process to sink in a little more. I guess there is no good eraser today. Now, I'm going to be focusing mainly on steps that actually involve step functions. Just want to be able to touch on all of these examples in the time that we have. So, attendance. All right, so for our second example, we have y double prime plus 4y is equal to sine t. And here, we already have a step function definition, so you don't do the turning on and off stuff. And then the initial conditions will both be 0. Now, those of you who are more up in your trig might find it strange that I wrote this as sine t minus 2 pi. Why is that kind of frivolous?
Because 2 sine of 2
That's not the reason. It is, but that's true, but that's not the reason. I think someone else. Yeah, sine's 2 pi periodic, repeats every 2 pi. Yeah, now if I'd expanded this using trig identity, then that would have come into play and given me sine t. But the reason why I wrote this way is to better fit the rule. Laplace transform of step function times function shifted is e to the minus cs f hat of s. Okay, so when we go ahead and transform both sides of the equation, well, for the second derivative, we're going to get s squared y hat of s. And normally we would have two terms in here for the initial values, but we don't have any initial values. They're both 0. And then we have 4 y hat of s is equal to, and now we have to transform this side. So Laplace transform of sine t, we have that on the upper board there. That is 1 over s squared plus 1. And then we have, so to fit this rule, because of a step function, we're going to have e to the minus 2 pi s times the Laplace transform of sine t. And the reason why I'm writing that here is to emphasize that though the function needs to be written in shifted form to apply the rule, you actually transform the unshifted version. So be careful about that. That's a possible stumbling block. And we know what that is. So now we have 1 over s squared plus 1 minus e to the minus 2 pi s. Another 1 over s squared plus 1. And so now we can just factor out a y hat of s over here. We get s squared plus 4. And so we can divide by that. And what we get is 1 over s squared plus 1, s squared plus 4, times, and I've factored out a 1 over s squared plus 1. So we get 1 minus e to the minus 2 pi s. So that is the transform of your solution. So questions about how we got this far? What would the partial fraction form of that look like? So with b over so I'm going to stay consistent with my notes. S squared plus 1 over s squared plus 4. And here again, it's best to try to match up like powers of s. This is going to go all the way up to a cubic. So if you have the 1 is equal to as plus b s squared plus 4 plus cs plus d s squared plus 1. So if you expand that and match up like powers of s, all the coefficients have to be 0 except for the constant term, which has to be 1. And I won't go through the whole algebraic process this time. This is on for my notes. And what we get is a and c turn out to be 0. So we end up not having any linear terms. And then b turns out to be 1/3, c turns out to be minus 1/3. Okay, so
Is A 0? Or is
d is minus 1/3. And my mind started going through the alphabet in order. D is minus 1/3. Okay, so now we can start inverse transforming. So y of t is now going to be the inverse transform of all of that mess with the constants filled in. So we have 1/3, 1 over s squared plus 1, minus 1/3, I have a wrong page. One over s squared plus 4 times 1 minus e to the minus 2 pi s. So if I call this part, just without these fractions, f hat of s, we need to inverse transform that in order to be able to do anything else. So for f of t, we're going to have a 1/3 inverse transform of 1 over s squared plus 1 minus 1/3 inverse transform of 1 over s squared plus 4. Okay. Now, fill in the blanks here. Sorry for the awful eraser. All right, this one we know how to do. We've seen it before today. Yeah, sine t. Okay. What about this one?
Cosine 2t.
No.
Sine.
Almost. Yeah, this most closely fits rule for sine. This rule, sine bt, but it's b over s squared plus p squared. Now, yeah, you can tell from the denominator that b is definitely 2, but you don't have the right numerator. So how do you compensate for that?
Multiply by 1/2.
Yeah, so, and a good way to look at it to reduce the possibility of mistakes is you need a 2 there for this rule to apply. That's your b. So go ahead and put it there, and yeah, then you multiply by 1/2. So you're going to get 1/2 sine 2t. That's how you should do things. You need something there, go ahead and put it there, and then compensate. Okay, brute force algebra. Okay, so now we have a transform of that, and therefore, this is the little f of t that we need. So when we distribute the 1 minus the exponential through here, well, this times 1, we have that. So we have 1/3 sine t minus 1/3, or 1/6 sine 2t. And then we have minus inverse transform of this, where c is 2 pi, and f hat of s is what I've labeled here. So since we've already gone to the trouble of inverse transforming this f hat of s, that's this right here, and this, just like the last example, what do I need to put for the final 2 terms? Because that's going to go to e to the, there's a step function times little f of t minus c. So this inverse transforms back to this. Again, you just have to fill in the particulars. And what will that give you?
Use of 2 pi.
Mm-hmm.
And 1/3
Mm-hmm.
sine t minus 2 pi.
Mm-hmm.
Minus 1/3 or 1/6
Mhm.
sine 2t minus
Yes, it would be. Well, I'll just do it like that.
Okay.
Cool. Okay. All right, and then you're done.
Then do what?
What? That's it. Yeah. So when you're handling the exponential, whatever you have here, figure out its inverse transform, and then whatever you got for that inverse transform, shift it by the value of c. So now this is not effective functions involved, but still you got to remember to do it in case it does matter. Okay. Right. So any questions about how that was polished off? Now,
So you put the whole thing next to the
yes, yeah, it needs to be in parentheses.
Okay.
Okay. Now, we have enough time for, well, the very last example in the whole dang notes.
Those other problems that online, you know how to do those. It's like 2 more.
The lowest one of a whole semester gets dropped. Yeah, generally they'll still have to be done. So, I mean, you may decide if you've done all the ones up to this point to forget the last one, but I put them out there because they deal with the same material that's practice for a final. You have until May 12th to get everything in. If you haven't done all the assignments up to this point, then you can make a judgment call. Also May 12th. May 12th is the last day for everything. Well, except the final, of course, because that's May 10th. But because I have to scramble over the weekend to get everything in by Monday, blah, blah, blah. Okay, so last example. Oh, a decent piece of chalk would be nice. So we have y double prime plus 3y prime plus 2y is equal to this piecewise function. So equal 1 until t equals 10, and then 0 after that. And 0 initial values. To express this as step functions, we turn 1 on at t equals 0, and then we turn it off at t equals 10. So that's right side expresses step functions to make it suitable for transforming. So what we get when we take the transform of the left side, we're going to get s squared y hat of s. And then the other two terms are not there because the initial values are 0. And then we have 3 s y hat of s for first derivative. And normally there would be a term for subtracting off y at 0, but that's not there. Plus 2 y hat of s. Bless you. And then on the right side, for 1, we have 1 over s. Here we have another 1 over s. And the step function of c equals 10 leads to the e to the minus, no, not t, s. Bless you. All right. So now we can go ahead and solve for y hat of s. We can factor this out. S squared plus 3s plus 2. Okay. The rest of the denominator, we have the s factored out. How's the rest factor? Yeah. Okay, s plus 1, s plus 2. Okay. So now that's the transform solution. Now we need to get it in a form where it can be inverted. What is the partial fraction form of that? In terms of constants A, B, C.
A over x plus B over x plus 1 plus C over x plus 2.
So now you get, so as you multiply both sides by the denominator, you get 1 is equal to A, s plus 1, s plus 2, plus B, s plus 2, plus C, s plus 1. Now, when there are linear factors, the easiest way to get to constants is to substitute the values of s and make any of those linear factors 0. So in this case, it makes sense to substitute s equal to 0, for instance. When you substitute s equals 0, the b and c terms will go away, and you're left with 1 is equal to 0 plus 1, 0 plus 2, 2a. So a is equal to 1 half. And then you substitute in s equal to minus 1. So the a term and the c term go away. So what you have is...
A be 1/3.
no, you're multiplying those, not adding.
Oh.
B equals negative.
Yeah, I've done worse. Okay, so we have b times minus 1 times 1. So b is equal to minus 1. And then finally you set s equal to minus 2. So the a and b terms go away, and this will reveal c. So you have 1 is equal to c times minus 2 times minus 1. So c is equal to 1 half. What's interesting is you see this pattern after doing enough of these partial fraction problems, that the coefficients, when the numerator is a constant, as it often is in examples like it is here, the coefficients tend to sum to 0. And we see that happen in this case. It's a good way to check your answer. But you can only expect that if the numerator is a constant. If there's something higher degree up there, like I could have a linear or quadratic up here, then you can't expect that to happen. Okay, so now we can write this as, and write this in a form which we could readily apply inverse transforming rules. Now, like I said, you're going to have a sheet given to you for the final that has the rules on it. It's in a textbook, so you already know what it looks like in section 6.2. You want to look it over before Friday, because there are a lot of rules on there. Not all of them you'll need. So have those useful trees in the forest picked out beforehand, instead of having to hunt for them while you're under stress. Okay. Okay. So filling in all the constants, so there's 1 half, 1 over s, minus 1 over s plus 1, plus 1 half over s plus 2. So we're just re-expressing the transform, and there's still this 1 minus e to minus 10s. So think of this as your f hat of s in your rule So you need to have this rule in particular burned to your brain, even though it will be on the sheet. So since you're going to need to apply that momentarily, we know that in this case, C is equal to 10. This is your f hat of s. So now you need to invert that to get your f of t. Now, the other rule that you'll need for this problem is, of course, the one we've been using already. Laplace transform of 1 is 1 over s. Laplace transform of e to the at f of t is f hat of s minus a. So that's the general rule. So now if we combine these two, Laplace transform of an exponential is just 1 over s minus a. So that's the pattern you're looking for when you want to inverse transform this. So when you inverse transform, just as part of the square brackets here, using these rules, what will you get?
Okay.
Mm-hmm.
What is e to the t?
Almost. Not t, but minus t. Because it's s plus 1, but we're looking at s minus a. So for this term, a is equal to minus 1. So it's e to the minus t. And then what's the last term? At plus 1/2, yeah, e to the minus 2t. So now you're going to use that to finish off the transform of the whole thing. So now you can write down your solution. So this times 1, that's already been inverse transform. So let's go ahead and write that down. Okay. And then we have minus from there. So now when you apply this rule, you have all the pieces. And you're starting from this and going back to that. You know what C is. You know what big f hat is. You know what little f of t is. So this, something of this form, is what you need to produce. So bring it home.
Use the t.
Mm-hmm.
T. 1/2.
1/2 minus e to the negative t.
Not just t.
T minus 10.
T minus 10. The shift goes in here. So yeah, you take this and shift it. T minus 10.
E
Minus 2.
minus 2t minus 10.
Yeah. Okay, that's it. I've come to the end of the notes. Okay. So any questions about how that was obtained?
Why is there a minus in front of u?
Oh, this is a fact.
Shouldn't the 2 on that be inside the parentheses?
Wait, which two are you talking about?
Right there.
The negative 2.
I'll
Shouldn't
make
the 2 be on the inside of the parentheses?
No, because what happens is you have minus 2t, and this is what gets replaced.
Oh, yeah.
So everywhere there's a t, you just put t minus c.
Yeah, and use parentheses to make sure. Yeah, actually, similar thing came up in the last example. That's 2 times you did 2t minus 4 pi, which is correct. But okay. Well, it's only 1 or 2 minutes left. Okay, so be sure to bring your questions about the final on Wednesday. That's all we're going to do.